The mechanistic target of rapamycin, or mTOR, is one of the most critical molecular switches in the regulation of growth, metabolism, and cellular survival. It acts as a nutrient sensor, orchestrating responses to food availability, energy status, and growth signals. While essential for development and tissue repair, chronic overactivation of the mTOR pathway has emerged as a central driver of aging and cancer, largely because of its inhibitory effect on autophagy, the cell's primary system for self-repair and detoxification. This makes mTOR both a powerful biological regulator and a high-stakes therapeutic target. Under conditions of nutrient abundance, mTOR remains active. It promotes protein synthesis, cell growth, and proliferation, processes beneficial during development and recovery, but increasingly harmful when unchecked in adult life. Active mTOR suppresses autophagy by inhibiting ULK1, the protein complex that initiates the autophagic process. As a result, cells prioritize building over recycling. In the short term, this may enhance cellular productivity, but over time, it leads to the accumulation of damaged organelles, misfolded proteins, and oxidative stress, hallmarks of both aging and cancer. In aging organisms, persistent mTOR signaling contributes to tissue deterioration by accelerating cellular senescence and preventing the removal of toxic cellular debris. The decline in autophagy allows dysfunctional mitochondria to build up, increasing reactive oxygen species and inflammation. This creates a tissue environment that promotes degenerative diseases and weakens the body's capacity to recover from stress. In parallel, elevated mTOR activity supports the survival and proliferation of precancerous cells by fueling growth even when quality control systems like autophagy are suppressed. This imbalance, too much growth, too little repair, becomes a breeding ground for both aging and tumorigenesis. This has led to growing interest in therapeutic strategies that modulate mTOR, especially through pharmacological agents like rapamycin and its analogs, rapalogs. Rapamycin works by inhibiting mTORC1, one of the two complexes that comprise the mTOR signaling system. By suppressing mTORC1 activity, rapamycin effectively lifts the brake on autophagy, allowing cells to clear out damaged components and restore metabolic balance. In animal studies, rapamycin has consistently extended lifespan, delayed the onset of age-related diseases, and reduced cancer incidence, making it one of the most potent longevity-promoting drugs ever studied. However, the therapeutic use of mTOR inhibitors carries significant risks and complexities. Inhibiting mTOR systemically can impair immune function, slow wound healing, and disrupt glucose metabolism. These effects may be tolerable or even desirable in the context of cancer, where suppressing cell growth is the goal, but in healthy individuals, chronic mTOR inhibition could accelerate frailty or impair resilience. This presents a serious warning. While targeting mTOR can extend life and reduce cancer risk in animals, applying this strategy to humans demands extreme precision and restraint. It is not a tool for indiscriminate use. Timing also matters. In early life, mTOR activity is essential for development and immune competence. Suppressing it too soon could impair growth or cognitive function. Yet in middle age and beyond, when the balance begins to tip toward excessive cellular burden and declining repair, modulating mTOR may offer protective effects. Intermittent or low-dose rapamycin protocols are currently being explored to minimize side effects while preserving therapeutic benefits. Alternatives like caloric restriction, intermittent fasting, and exercise also exert mild, natural inhibition of mTOR, offering safer ways to promote autophagy and delay aging without pharmacological intervention. The implications for cancer are equally nuanced. Many tumors exhibit hyperactive mTOR signaling, often due to mutations in upstream regulators like PI3K or AKT. In these cases, mTOR inhibitors can suppress tumor growth and restore sensitivity to other treatments. However, not all cancers respond predictably. Inhibiting mTOR can activate feedback loops that trigger alternative survival pathways, or even promote resistance in some tumors. Combination therapies, targeting mTOR alongside other vulnerabilities, are being developed to address this problem, but results remain mixed. As with aging, the cancer application of mTOR inhibitors must be carefully matched to individual disease profiles and molecular characteristics. In sum, the mTOR pathway represents a powerful but double-edged force in the biology of aging and cancer. Its role as a suppressor of autophagy makes it a central link between nutrient sensing, cellular cleanup, and disease progression. Overactivation drives unchecked growth and impaired repair. Inhibition can restore balance, but at the risk of compromising vital functions. The future of mTOR-targeted therapies lies in precision, identifying when, where, and how much to modulate this pathway to promote longevity and suppress cancer without undermining health. With continued research, we move closer to that delicate calibration, where growth and maintenance are no longer at odds, and the potential for healthy aging becomes a practical, measurable reality.